So we spoke about really simple unifactorial linear relationships till now. So we had a y that is a function of x and only one x. We're going to talk about multiple regression soon, where we have, which is a more realistic approach, where we have one factor that's changing, the variable that's changing, the y, is actually a function of a few things that are causing it to change. So if we think about plant growth, y is the stem extension rate, and x can be the nutrient levels in the soil and the water in the soil and the amount of light, you know, I mean, like, so in real life, usually we deal with things in a multiple regression format. So we looked at linear relations, and we saw them with the Pearson's coefficient as well, which is really just about whether a linear relation exists between an x and a y. But we're going to pause a minute and discuss nonlinear relationships, because a lot of our data is nonlinear in nature, and there are ways to deal with this, which is either conducting nonlinear models of regression or being able to transform our data in a way that makes it linear, and you'll see what I mean in a minute. So often our data is related, y and x are related, but not in a linear relationship. So we can see the parabolic relationship up here. So y is clearly a function of x, but it's not a straight line. So we can still do a regression model. We can use a nonlinear regression model where y is a function of x squared in this case, or we can transform our data to make it linear. So if y is a function of x squared here, y is also, I can take the square root of that and have y as a function of x of the square root of x squared, and that will give me a straight line. Okay, so I can transform data to create a linear relationship, and then with linear regression, I know what to do really easily. Another approach is to apply nonlinear models, and ones that are, here, I'll make that a bit smaller, nonlinear models with relationships we already know. So if you do chemistry, you'll be aware of the Michaelis-Menten plot, which is the thermodynamic reaction rate of enzymes as a function of the substrate concentration. You fit a certain function to this relationship. So initial reaction rate, the rate that the enzyme works at, is related to the substrate concentration. And this relationship has a really clear look to it that's to do with the biochemistry, and it can be described in a nonlinear equation. So here we have V, the y is a function of x of the concentration. So when you have square brackets around something, it's the concentration of the substrate, and here is times V max, which is some parameter that describes this function, and Km. So this is the rate, Km is the substrate concentration, where the reaction rate is half of the maximum, and the maximum is up here, that it's asymptotic in this case. I can also fit in nonlinear regression models to things like niche functions. So there's an optimum temperature for us to function in, and we can tolerate higher and lower, but we have a certain niche, a certain zone that is conducive to life, right? The same with pH. There will be some rate of reaction or distribution of some species, and it will have an optimum, and it will look a bit like a bell curve around that. That's called it. This is not, you don't get this confused with the normal distribution. Okay, we're not talking about distributions, we're talking about y as a function of x, but it looks the same, right? It's like this bell curve. And this is what we call a quadratic equation. So we can fit one of these to our data. Okay, so instead of having a linear equation where we know y is bx plus a, we have some sort of other function that we can fit. Okay, so many times, and we'll see this in a minute, but many times within your field and your discipline, there will be a set of these equations you fit your data to extract parameters you're interested in. So for example, I would extract this because I'm going to have, I'm going to measure the rate of reaction at 3 and at 4 and at 5 pH and at 7 pH. And what I'm trying to do is to work out, for example, what is the optimum pH? I might have not hit it with my experiment, okay? But if I fit this quadratic equation, I can extract the parameters that I get from it, okay? So it's a really powerful tool. I can also work out where growth can't happen anymore. Even if I haven't measured at 10, I can work out what's happening, what is the rate of reaction at a pH of 10. So what do I do if I have nonlinear relationships? One way is to transform my data so that I can use linear regression, or I can describe it linearly, because that really is the simplest form of a relationship. So I can think about things like AA here as a function of AA. Okay, so AA is my variable, and if I plot it against AA, I'll get, of course, the one equals the other. I'm getting a perfect linear relationship between the two. AA squared against AA would look like that. 1 divided by AA against AA would look like that. Log AA would look like that. And what I'm trying to do is make it look like this one up here. And what I can apply to my relationship is a transformation of one or both of the variables so that this relationship is linear. And usually what I need to do is perform the opposite operation, right? So if I had 1 divided by AA, to get back to AA, I need to multiply by AA, right? So for example, here is AA predicting BB, okay? So BB is a function of AA, and I can see there's this, this is the data, and here is my relationship between them, and I can see that this is an exponential curve, so y is growing exponentially relative to x. And how do I go the opposite way? I take the log of BB, okay, of y, and I apply that. So if it's exponential, I'm using the natural base, the e, and what I will get then, if I plot AA against the log of BB, is I'm going to get a nice linear relationship. Okay, so I'm allowed to do that, and that's called a transformation from nonlinear to linear. And to summarize that, we have many nonlinear relationships already described. So your data might fit and should fit relationships that are relevant to your field. So we have, if you're working on growth rate of bacterial populations, or many other, so bacteria proliferate by doubling, right? Because each one splits into 2, right? So we have doubling of the population all the time. So this is a logarithmic type of relationship. So if we look at time versus the bacterial population, it will be logarithmic, at least in part of the range, you know. And then you hit problems of you know, carrying capacity, how much food is around, density, issues that affect that. I mean, I said it will plateau, but it will have the logarithmic phase in it. If you work on radioactive isotopes, which a lot of us do because we use that for dating, dating materials. So if we want to know how old a rock is, or how old a soil profile is, how old is a fossil, how old is a finding we have, we can use radioactive isotopes that slowly lose some of the one of the isotypes, and we can look at the decay rate. And usually we just measure a few points, right? But we fit it to a type of exponential curve, and from that we can work out half-lives, how old our sample is, things like that. So decay rates would be fit to an exponential curve, and that has parameters that are known. We saw the Lorentzian curve, or the Gaussian relationship, the bell curve, which is very frequently used in niche models or in anything where we're looking at tolerance. So there is always kind of an optimum. So our body is optimized to work at around 37 degrees, and we can still function up to 42. We can still function down to 30 probably. But like as we go out of that, we can't survive, and when we deviate from our optimum, you know, you feel ill, right? I mean, like, you're not functioning to the same level. And chemical reaction rates, those of you who are into chemistry or biogeochemistry use a lot of their own equations. One of them is the Michaelis-Menten that we looked at. So you often know what type of relationship you're working towards a priori. So you would know because you're looking at, you know, decay. You're looking at dating an object using carbon-14, for example, radioactive decay. You know you're going to need to fit it to an exponential equation. So you usually know the type of relationship between x and y for your study. So when you have this nonlinear relationship, so the same way that we described the linear regression, we knew what the equation is going to be. Okay, so I know what type of relationship I have. I have a straight line, so it has y equals a plus bx. But what exactly that relationship is, I'll need to calculate the values of the parameters a and b. So I have x and y are the things I've measured, but to get what the line is, I need to calculate the values of the parameters a and b, and we did that by making the line go through the means and reducing the sums of squares, and we extracted what is the slope of the relationship, what is the intercept of the relationship. And the same thing exactly happens with parameters for these nonlinear relationships. So I'll give you some examples. Now, another thing to take into account first is that many relationships and many types of data, I can have different relationships happening at different parts of the range. So I can see things like this is oxygen uptake, okay, when we do a 6-minute walk test. So at first, we're rested, right? I have a period where I'm just sitting there and resting, getting a baseline. And then I start exercising, okay? So here the type of relationship is different, okay? So I'm getting this kind of, there are 3 phases, okay? So we have basal level, and then we have an asymptotic rise in our consumption of oxygen until we reach a plateau, and that's where we can't, you know, we can't give anymore. And then we have a slow decrease, an exponential decay, if you'd like, back to a recovery phase. So in many of our time series, especially, or in we focus on a certain part of this curve, and so our non-linear model is often not for the entire range of data. So I can give you another example of parameters. So just like we had A and B in the linear model, in this Gaussian curve, in the Lorentzian curve, in that bell-shaped one, f, which is the function of x, which we also call y, right? Whatever is a function of x is dependent on x, of course, and then a bunch of other parameters. So we have e, which is the exponent, right? And a, b, and c are the parameters I need to estimate. Now we'll talk about how this estimation comes about in the next lecture, and we'll also, I'll give you some further examples.